Good morning, class. We're looking at our notes for 1.3. I'm totally not on the top page. Let's dig through here and see if we can find the right one. It looks really long, but it's really probably, with me doing the notes, about 20 minutes of uninterrupted notes. And remember, I have my posted notes video as well. So if you're kind of following along with this and you think it's too fast, you could always go and check that out. So it didn't print well. I'm printing from home. But what this shows here, this property, it says, and these are basic limits. So we're looking at evaluating limits analytically. And so first we're just going to look at some properties that we're allowed to use. And maybe I should just zoom this in a tiny bit as well. So some of our limit properties. If I have the limit as x approaches c of b, and b is meant to be a constant, the limit is just that number. It's just b. So the limit, say, as x approaches 0 of 7 is just 7. Over here we have the limit as x approaches c of x. So because I don't have anything weird there, we could just directly substitute and get c. And then we can do the same thing if I have an exponent. If I have x raised to a power, I can just go ahead and substitute directly and find that value. I also have some properties over here. So if my limit is, if I'm taking the limit of something and the function is being multiplied by a number, I can take and multiply that number by the actual limit of that function. We can take two different functions. When we're finding the limits, we can find them separately and just add or subtract. If the functions are being added or subtracted, we could add or subtract those limits. We can take functions that are multiplied together, take their limits and multiply those. Same thing with division. So it's not stuff that we use a lot, but sometimes you'll get a math problem, a limit question, possibly, is where it would come in, and you're just stuck, and it's going to go back to these properties. So the first one, we're going to do this horrible long way, just so you can kind of see what these properties allow us to do. And what these properties will allow us to do is say, oh, it's being added, so I need to break this apart, make it the limit as x approaches 2 of 4x squared plus the limit as x approaches 2 of 3. And then my first one, it's a 4 times x. So I would want to say, well, that's, or sorry, 4 times x squared, that's that scalar multiple. So I'd say 4 times the limit as x approaches 2 of x squared plus limit as x approaches 2 of 3. And then above, it tells me if I have an x squared, well, that's an exponent. X is being raised to a power. I can go ahead and substitute directly. So 4 times 2 squared plus, and then over here, my limit as x approaches 2 of 3, well, that's a constant, so it's just going to be 3. Let's see, this is going to be 4 times 4 plus 3. So we're going to get 19 as an answer. So really, we could have just directly substituted in the entire thing to begin with. That's what we will normally do. But the goal here is that you kind of understand why we're allowed to do that and that we're using these properties actually. So in the next one, I have a fraction. Sometimes I might try to factor them, but this says the limit as x approaches 1, and my denominator is 1 plus 1. So that's totally fine. I don't have to worry about it. I guess I could use these fractions, and I could find my limit of the top, the limit of the bottom, but I think we've had enough breaking limits apart. So because it does not make my denominator 0, I can directly substitute. 1 plus 1 plus 2, that's going to be 4 divided by 2 is just 2. And as always, remember, denominator, that means I can't have x equal to -1 because x plus 1 can't be 0. And depending on, like if this was x plus 1 was a factor, we canceled out of the top and bottom, it would create a hole. Otherwise, we'd have an asymptote. And so you always kind of want to look at factoring if you're trying to figure out that information. But I don't think our numerator can't even be factored, can it? So that means this is going to be an asymptote. So because it's from the denominator, it would be an asymptote. But again, if I could factor and cancel out a factor of x plus 1, I would have a whole. All right, so looking at the next two problems. So now we're looking at some kind of weird stuff. This again is not, we can just directly substitute into these limits. But what they're trying to kind of show here is we've got stuff about limits involving radicals. So they're saying you can directly substitute, but we can directly substitute if we have an odd root or if our square root is even, but what we're taking the root of is greater than 0, which we kind of already knew, right? We can't plug in a negative number for x anyway, so that kind of makes sense. It follows the rules we know. And here they're talking about how if I have a function inside a function, I can take the limit of the inside function and then evaluate that. So just kind of how we can do a limit of a composite function. And that's what we're doing a little bit here. You'll see that this is my limit as x approaches 0 of x squared plus 4, and this one's my limit as x approaches 4 of just the square root of x. And this is like my square root thing, but like the x squared plus 4 is inside. So kind of just following what this is. So my limit as x approaches 0 of x squared plus 4, well, I could directly substitute there. 0 squared plus 4 is just 4, so that one equals 4. And then over here, my limit as x approaches 4, so it's no coincidence here that this is a 4, this is a 4 of x, of the square root of x would be square root of 4, that's just 2. So basically what they're saying is you can see that this limit matches up with this number, right? And so it's almost like we took this answer and we plugged it in here. So because these two combine, like when I took my output from this one and kind of put it into that one and the answer was 2, I already know that this whole thing's going to be 2. But if I was given a problem like this, I would not be breaking it down, right? We would just say, oh, I can directly substitute, and that's what we'd be doing. But it is kind of cool that you can use that property. It's just not useful in this question. So over here on the next one, same thing. This is a cube root, so I can plug in any number for x. So I'm just going to directly substitute. We could use these properties again, but I don't know how much it's worth really spending any time on it. I mean, I think it's one of those things you do it once. Oh, here's something that's picky. I should not write limit once I substitute a value in. So I'm finding my limit as x approaches 3, but now I'm substituting in 3, so I should be dropping that limit statement. So let's get rid of that. So that's probably the best part of this whole problem, is that you can remember things like that. So 2 times 9 minus 10, let's see, that's 18 minus 10, that's just going to be 8. Notice we're showing a lot less work this year in calculus. It's kind of more your comfortability level with some of this. So this is our first page. All right, so looking at our next page of notes. So this is kind of where we get into the nitty-gritty here. So what I've got here is we've got limits of trig functions, and you're going to see that these are all pretty much just you find the limit by substituting the value, right? But we have to be careful. Obviously, sometimes we might have something that's like a 0 or whatever. So we do have to be careful of that. Let's move this quart out of the way. So limit as x approaches 0 of tangent x, I'm going to substitute 0 in for x. And then to evaluate it, oh, we got a little bit of noise in the background. This is a 0 degree angle, right? I'm finding the tangent of 0, so 0 radians or 0 degrees. It's going to be this point right here on my unit circle where my radius is 1. The point's 1, 0. This is an xy. Tangent is y over x. So 0 over 1 is just 0. So this is probably way more detail than what you need, but I'm just trying to preemptively kind of jog your memory on this. Next one is as x approaches pi. So let's go ahead and substitute pi. And then that means I have a point right here, which is at negative 1, 0. And that's my xy. My r is 1. So cosine is x over r, which is negative 1 over 1. Okay, so my cosine of pi would be negative 1. This is going to be pi times negative 1, which is negative pi. Last one, I've got the limit as x approaches 0 of sine squared x. So that means we're looking at a limit as x approaches 0 of sine x quantity squared, right? That's what that means. And I think sometimes people confuse those. So I need to go ahead and substitute. I want to find the sine of 0 and then square it. So what I should do is draw another graph. And this is the same graph that I had over here, right? Really, I could use that one. But this time, my sine is going to be y over r. So y over r is 1 over 0, which is just going to be 0. Or sorry, y over r is 0 over 1, which is just 0. And so 0 squared is 0. So we've got that limit as well. So remember, anytime like here I left the limit in there because I still had x, once I get rid of that limit part, or once I substitute, I get rid of that limit statement. So be careful about that. Let me get all these, so many papers out of our way now. All right, so for the bottom ones, we're looking at now finally strategies for finding limits. So this is the stuff that I think you should have done last year, but maybe we didn't do last year. So we had a fraction on the front and we said, oh, it doesn't make the denominator 0, we can directly substitute. But this time when I substitute 2 minus 2 makes a 0 in the denominator. So that's when we've got to look at strategies. So one of the first strategies is factoring. So I'm going to write limit as x approaches 2. X cubed minus 8, I can think of it as x cubed minus 2 cubed. So that follows a pattern for difference of cubes. So I could go ahead and factor that. So that's going to be an x minus 2 times, and some teachers teach this as SOAP or as, what's another one? Mothership, othership, or a SOPS pattern. So there's a lot of different ways to teach this. So basically what's happening is we take that x and we square it. This is going to be opposite product. So 2 times x is 2x. And then this is always positive. And then 2 squared is 4. So, and this is not going to be further factorable ever on a cubic. So my denominator is an x minus 2. So now I can see I've got a factor of x minus 2 in numerator and denominator. Remember, that means we have a whole at x equals 2. That's what that means, just to kind of go back and tie this into Algebra 2 and pre-calc. So I still have a limit in here because I have not directly substituted yet of x squared plus 2x plus 4. At this point, I don't have a denominator. I can directly substitute. So remember, a limit it doesn't matter if there's a whole. For limit, you just have to be close. So it's okay if there's a whole at 2. I can still evaluate this. Right? Think about this graph here where we have a whole, but my limit is what value do we get as we're approaching. So it doesn't matter that there's a hole there. And obviously this graph is a parabola. It doesn't look like this. But this is just kind of to get you thinking. So now we'll directly substitute 2 squared plus 2 times 2 plus 4. Let's see. This is 4, 4, 4, which is 12. So we've got our answer. All right, next one. We have the same issue. If I have negative 3 plus 3 in my denominator, it makes a 0. So I cannot directly substitute. So let's go to factoring again. And because I am not substituting yet, I have to keep rewriting limit. So my numerator is going to factor to x plus 3 times x minus 2. So we have a whole again at x equals negative 3, which is fine. So now we have a limit as x approaches negative 3 of x minus 2. Directly substitute, answer is negative 5. So sometimes we want to factor. So these strategies are when direct substitution doesn't work. And the strategy we're using right now is we're using factor. And divide out, right? Basically, we're dividing this out of the numerator. Or we're dividing this one out of the numerator and denominator. So we're factor. The next strategy we're going to look at, we looked at this one the other day. I have a square root. So what I want to think about is rationalizing. So basically multiplying it by the conjugate. So instead of rationalizing the denominator, we're rationalizing the numerator. If we can't directly substitute, I always check that first. So this is a limit as x approaches 0. I can't put 0 in the denominator. So I am going to have to go ahead and do this strategy. So I want to multiply the top and bottom by square root of the quantity x plus 1 and then plus 1 instead. That's my conjugate. If I have a minus 1 plus 1, we will multiply that on the top and bottom. Okay, so in my numerator, when I multiply this one times this one, right, it becomes squared, so just an x plus 1. When I multiply it by the plus 1 and then the minus 1, they zero out. But negative 1 times 1 would be a minus 1. And my denominator is x times all that stuff. You never want to distribute in that whatever that is to the denominator, because our goal is to, that x was, I didn't like it there, so my goal is to like cancel that out basically. So I'm left with x in the numerator, x times all that stuff in the denominator. So we can kind of see where this is going. Our factor of x is gone, and my numerator will have a 1. Okay? And so now at this point, I can directly substitute. 0 is no longer going to be an issue. So 1 over square root of 0 plus 1 plus 1. So that's going to be 1 over 1 plus 1, which is going to just be a 1/2. All right, so our strategy on this one is rationalizing. All right, last page is the squeeze theorem first, and then some special limits that we need to kind of memorize, but like, let's be honest, we'll be memorizing it again before the AP test. So the idea behind the squeeze limit is we've got some function, and you can see our function f is in the middle on this graph. Like, I have a function above it, I have a function below it. And the idea behind the squeeze function is I have this one up here, it looks like a g. I have g, and I know the limit. And the limit is this number right here. I have h, and I know the limit at this point at c. It's also the same number. So g and h both have a limit at c, and they are both the same number. But I know that f is squeezed between those two functions. I know if I graphed it, it'd be between. So maybe f has some weirdness, and I can't actually find its limit, but because I know the limits of those other two, and it's that same value, and f is between them, f must have the same number limit as well. So that's what they're showing here. So we have h of x less than or equal to f of x less than or equal to g of x. So remember, when we talk about h of x, f of x, g of x, we're talking about the y values. So that means like the y values for h are below the y values for f, and then g has the y values above that, right? And we're interested at c. As x approaches c, my h of x has a limit, and that's the same thing as my g of x at c. So they both have the same limit at c. And because f is between them, it must also have that same limit. So that's the second term. I think it's only been on the AP test like maybe one time, if I remember correctly. It's not a super common thing, but it's definitely worth talking about. I think what's harder is knowing when to apply it. And so it is going to pop up a couple times this year, so you get to see it. So we've got these two special trig limits right now. I feel like we don't use this one as much. You'll maybe use it a tiny bit. It's usually this one. But they're not going to give you that limit, just sine x over x. You're going to have to work for it a little bit. So on this one, it's my limit as x approaches 0, which matches up here, but I have tangent at x over x. So it's my job to think, well, hey, I can take tangent and I can rewrite it using sine. So my first job is to rewrite this as limit as x approaches 0 of, we know tangent is sine over cosine, so sine x over x cosine x. All right, now I can see that the sine x over x, that's the part I want. So I'm going to write sine x over x, and then I've got 1 over cosine x. So we saw on that first page that if we have two limits being multiplied, really what we could do, or a limit of two functions being multiplied, I should be careful the way I say that, is we can take and find those limits separately and then multiply them together. So this first limit here is just going to be 1 by this property up above. So that's going to be a 1 times. The other one I can substitute 0 in for x. So 1 over cosine 0. So remember, I'm not dividing by 0. I'm dividing by the cosine of 0 radians. So think about where 0 radians would be. And so my cosine would be 1. 1 times 1 is going to give us 1 for an answer. Moving all these pages out of my way. I made a big mess earlier. Okay, last math problem. So what we need to understand on this one is it doesn't have to be sine x over x, but whatever I'm taking the sine of here needs to be the same as on the denominator. So on the next one, we have a sine 4x. So in order to use that property, I need a 4x in my denominator. So that means I'm going to write limit as x approaches 0 of sine 4x over 4x. But I can't just go around multiplying 4 only in the denominator. I'd have to also multiply it into the numerator. So what I did is I multiplied the top and bottom of my fraction by 4. So now we know we have this thing where if I have a limit and it's being multiplied by some kind of scalar factor, so that means like it doesn't have a letter in it, right? Just a number. I could go ahead and put that in front so I can find the limit and then multiply by 4. So it might help to think this 4x divided by 4x, or the sign of 4x divided by 4x. I can't just cross those out and make them a 1. My alarm's going off. I think I'm supposed to wake somebody up. What I could even do is I could write limit as, like I could make this a y, right? I could substitute something in and I could say something like this, if that makes you feel better. This step is not necessary. At this point, I can say, well, this limit equals 1 by that property, and 4 times 1 is just going to be 4. So hopefully this helps you with some kinds of tricky limits. I hope it's review, but if it's not, I've given you a lot of information. Please ask questions in class if you have them.